Hi guys, welcome to this set of videos. What we're going to do here in this set of videos and this section of notes is we're going to go back to a topic we've already discussed. That topic is dilations. Now, what we would have done way back in the sort of the beginnings of your geometry course, for us what was chapter 1, is we talked about transformations and we mentioned dilations when we were talking about transformations. Remember, transformations are things like a translation, just a change in position. There was also reflections. That's where we take an image, right, and we reflect it across an axis, across an x-axis or a y-axis, generally is what we reflect it across. And then we also talked about rotations. In that same chapter, we mentioned dilations, but we didn't do any dilations. And hopefully what you'll recall is it was because of this. A translation, a rotation, and a reflection were rigid transformations. Rigid simply meaning that the image and the pre-image were congruent. Remember, congruency preserves both shape and size, right? So whatever figure you started with, the figure you end with will be exactly the same figure. If you start with a triangle, you're going to end with a triangle. If you start with a circle, you're going to end with a circle. Start with a square, you're going to end with a square. And not only will you have the exact same shape, but it'll be the exact same size. It will just be moved somewhere else. So that's why we eliminated, or that's why we didn't do any dilations back when we first started talking about transformations. And it was because a dilation does not maintain congruency. When you do a dilation, you will change the size of the figure. Now, it'll still be the same shape. If you start with a triangle and you do a dilation, you're still going to have a triangle. It'll just be either a bigger triangle or a smaller triangle. So, what you hopefully then recognize, or if you didn't, I'm going to point it out to you now. So far, everything we've talked about here in your geometry course has been dealing with congruent figures, which is why we didn't spend any time talking about dilation. We've been talking about congruent angles, we've been talking about congruent lines, we've been talking about congruent triangles. You probably just got done talking about congruent quadrilaterals like parallelograms and squares and rectangles and rhombuses, kites, things like that. Well, now what we've done is we've gotten to a point in geometry where to go a little bit further, we need to talk about dilations. And so that's exactly what we're going to do here in this set of videos and these notes. So a lot of what we're about to do, hopefully you'll remember from, actually for us, what was all the way back in chapter 1. Chapter 1, most of the stuff you're going to see here is being pulled in from that chapter. Really, the only difference is now we're going to introduce again this idea of dilations and not just let you know what it is, but actually do some dilations. So, with that in mind, here we go. Our essential question for this set of notes is going to be, how does a dilation transform a figure? And like we just said, we know that a dilation will either make the figure bigger or smaller. What we mean is it'll change its shape. And the way that we're going to do that is we're just simply going to explore a little bit about how the transformation of a dilation and what it does to a figure. So let's jump right into this. Here we go. A dilation. All right, here's what we know about a dilation. A dilation is a transformation that will change the size of a figure or a polygon, but it'll leave the shape unchanged. And like I just said, if you have a triangle, after a dilation, you're still going to have a triangle, right? That doesn't change. If you have a rectangle and you do a dilation, you're still going to have a rectangle. The only difference is we'll be changing the size of the figure, either making it bigger or we're going to be making it smaller. Now, a couple of things we're going to talk about here when it comes to dilations that'll be really important. And rather than highlight it, I'll just simply underline them. There's going to be something we're going to talk about called a center of dilation. We'll actually talk about the center of dilation a little bit later. Right now, what I want to talk about is a scale factor. So again, this center of dilation, which I've got both of them here, center of dilation and scale factor, we'll come back to this center of dilation, but let me first here real quick mention to you just what is it. So the center of dilation is a fixed point about which the points of the dilation or the points are being transformed by the dilation. And again, we'll talk about that a little bit more later so that makes sense. But you guys hopefully remember when we did reflections, right? You needed to know which line you were reflecting the image over. Were you reflecting it across the x-axis or across the y-axis, right? What line were you using as your line of reflection? When we did rotations, right? You needed to know that we were rotating either clockwise or counterclockwise, and you needed to know that it was about the origin, right? There were certain things you needed to know in order to perform those transformations. This is no different. In order to do a dilation, you need to know what point that dilation is being done around. So again, we'll talk more about that later. And then another thing that you need to know is this idea here of a scale factor. So the scale factor is the ratio that will give you the lengths of the corresponding sides of the image and the pre-image. Okay, so let's park here and talk about scale factor for just a minute. First, the scale factor is always going to be given the, what's the word I'm looking for here? Not a variable, because we know it's going to be a scale factor. Symbol. We're going to use the symbol, actually, we're going to use the letter K to represent scale factor. Scale factor is going to be a lowercase k. So you're actually going to see lowercase k's quite a bit here in this chapter, and every single time that lowercase k will be telling you what the scale factor is. Now, I told you there are two things that we can do to a figure. We can either make it bigger or we can make it smaller. This should make perfect sense here as I explain it to you. If k, that scale factor, is a number greater than 1, right? We're talking a number bigger than 1, 2, 3, 4, 10, 100, a million, whatever. As long as that number is bigger than 1, what it's going to do is it's going to enlarge the size of the pre-image. We're going to be making our figure bigger. This is an enlargement. And then, right, my only other option, right, is if k is less than 1. But of course, we don't want it to be a negative number. That doesn't make any sense. So if your k is less than 1, that means it's a fraction, but it can't be negative, so it's got to be greater than 0, right? So all numbers between 0 and 1 are fractions, right? Something less than 1, you know, 0.5 or 1/2, 0.33 repeating or 1/3, right? These are great examples of a scale factor that's less than 1, can't be less than 0, won't be negative, it's got to be between 0 and 1. But if it's between 0 and 1, this is going to shrink the original figure. It's going to make it smaller, which of course we will call a reduction. Right? So that's the idea behind a scale factor. It's going to be given the symbol k. It can either enlarge the object if k is greater than 1, or it will make the object smaller if k is a fraction, a number between 0 and 1. So let's talk about the two figures that I gave you. First, please notice they're both triangles, right? They're going to be the same shape. And this is really, really important about dilations. A dilation maintains angle congruence. So here's the really, really important part. All angles are congruent. And that makes sense. If I change the measure of the angles, then I'll no longer have the same shape. That's changing the shape. And we just said up here, right, that a dilation will change the size, but it doesn't change the shape. So that means the angles have to be congruent from one object to the other. Even though it's getting bigger or smaller, the angles will not change. Now, the only way that you could measure those angles is if you had a protractor and you laid a protractor on there and did it. So for now, what I'll do is I'll just give them to you. But angle A is 22 degrees. And if you were to lay a protractor on the smaller shape, you would find that angle A prime is 22 degrees. Right? And that's going to be that way for all of them. Angle B is 33 degrees. And angle C is, of course, obtuse, so it's going to be greater than 90. It's 125 degrees. And the same is true for B prime and C prime. B prime is going to be 33. You could put a protractor on it and measure it. C prime is going to be 125. You could put a protractor on it and measure it. So we could just simply say is congruent to the angle B prime. Is congruent to the angle C prime. The angles cannot change. If you change the measure of the angle, you're changing the shape. And a dilation doesn't change the shape. It only changes the side, or the size. So, Freudian slip there, what does a dilation change? Well, the dilation will change the length of the sides, right? So, lengths will change. Here we go. Let's talk a little bit about this. First, in my triangle, AB. So in this triangle right here, my larger triangle, I have AB is 6. So that is 6. I have AC, again, you could use a ruler to measure these, is 4. And CB or BC, whatever you want to call it, is 3. Great. In my smaller triangle, the one that I have reduced in size, AB is 3. Let's see, AC is 2, and BC, or CB prime, whichever way you want to do it, it's the same thing, is 1.5. Okay, now, here's the point with the dilation. Dilation is going to be all about proportions. We're going to talk a lot about proportions as we make our way through this chapter. Proportions simply means, right, comparing corresponding sides. All right, we need to compare the lengths of corresponding sides. But we need the proportion of the lengths of corresponding sides to all be the same. And I know that that's a mouthful. It's actually a little bit easier than it sounds. Here's what we're going to do. First, proportions. So I know that side AB and A prime B prime are corresponding sides, right? Those are the corresponding sides in these two triangles, just like BC and B prime C prime are corresponding sides. A, C, and A prime C, right, corresponding sides. So I need to find the proportions of those sides. Well, here we go. I will do, let's see, do I have enough space there? Actually, here, let me slide this down just a smidge, and I will do it right up in here. So, there we go. There's my shapes, right? So I'm going to do AB, right? So AB, remember a proportion is just a ratio. So I have AB, and then I'm going to divide that by A prime, B prime. Right? There's my proportion, right? Okay, let's do again. Well, my proportion, my ratio, right? Ratio is just a fancy word for a fraction. So I'm going to find, right, what is the, essentially the scale factor, right, that I used to do this dilation. The next one I could do is, sure, let's do AC. So we'll do AC, divide that by A prime, C prime. And then the last one is BC. BC over B prime and C prime. Okay, so let's go ahead and figure out what each of these is. Keep in mind, I need them all to be the same ratio. I need all of these proportions to be the same. So here we go. A, B is 6. A prime, B prime is 3. 6 divided by 3 is 2. Okay, what about the next one? Well, AC is 4. A prime, C prime is 2. So that'd be 4 over 2, which again is 2. So far, so good. We're looking great. Both of these have the exact same ratio, a ratio of 2. Well, what about my last one? BC, which is 3, over B prime, C prime, which is 1.5, and yeah, sure enough, use a calculator if you need to. 3 divided by 1.5 is 2. This right here is the really important part. In order for it to be a dilation, I need all of those ratios to be the same, and that is your scale factor. Scale factor K equals 2, right? And it's not that hard to see. You can really pretty simply look at it and recognize if the length of this side was 6, I simply divided it by 2 and got 3, right? The length of the side was 4. I divided by 2 and I got 2, right? So it is a reduction in size, and my scale factor was 1/2, right? I just take the length of each of the sides, divide it by 2, and there you go. All right, so that's what a scale factor is. Again, we'll come back to center of dilation in a second. So let's talk about the properties of dilation, and then we'll go ahead and do a few more example problems together. Okay, so there are several things that a dilation must preserve. We already talked about the fact that it must preserve angle measure, right? If you change the angles, you change the shape, and that's not how a dilation works. It only changes the size, it doesn't change the shape. It also preserves betweenness. This is an interesting one. Let me quickly here talk to you about what betweenness is. It's not difficult. Betweenness is simply this. If I have point A, point B, and point C, right? Each of those points is a certain distance from each other, right? B is, I don't know, maybe right in the middle of A and C, whatever, it doesn't matter. It's a certain distance, right? B is a certain distance from point A and a certain distance from point B. A dilation cannot change those distances. It cannot give you all of a sudden point A, point B, and then boom, point C is now all the way over here, right? See how it's changed the distance between B and C? Didn't change the order of them, right? It didn't move any of them. They're all still in a straight line. It just simply changed, right, one distance more than another. That is not how a dilation works. It cannot change the betweenness. Then it cannot change the collinearity. This one's actually really simple as well. If I have point A, point B, and point C, and they're all in a straight line, right? They're all in a straight line. They're collinear points. A dilation cannot change collinearity, simply meaning, right? It's not going to just all of a sudden move a point out of that straight line that I had before, right? These are collinear, these are not, right? A dilation is not going to do that. If you have 3 points that are collinear, after a dilation, they're still going to be collinear points. They have to be. And then